a student who's going to tell us about the Kronecker product of Schur functions.
Introduce me. So I'm gonna talk about the Kronecker product of Schur functions today. And
Wait, even the microphone doesn't work?
my keyboard don't work.
Oh, fun. So she's going to talk about it off the cuff with no slides. There you go. Can you make that little thing go away? I don't mean to complicate
This
things.
is part of the room.
Oh,
There we
oh, hey, you did it great. Awesome. Proceed.
So here's an overview of all the topics I'm gonna cover today. I will start by introducing the Kronecker coefficients, and then we are going to talk about the positivity the tensor square conjectures, for example. And in particular, we study the tensor square of square shapes, and we're gonna show some results we have on those. And lastly, I want to talk about some open problems related to the saturated Newton polytope and the Kronecker product of Schur polynomials. Okay, so start with the Kronecker coefficients. Let's do some quick review. So we start with the symmetric group, which are a group of permutations equipped with the composition. And the irreducible modules of the symmetric group are the spec modules. Those are indexed by the integer partitions, which are a sequence of weakly decreasing positive numbers that sum up to n. And so a question we may ask is, what happens if we do the tensor product of two spec modules? And because we're still gonna get a representation, we can write it, we can decompose it into irreducibles. And the Kronecker product are therefore defined as the multiplicities of the spec modules. For instance, the Kronecker coefficients G, lambda, mu, nu. They are the multiplicities of the spec module for nu in the tensor product of S mu, S lambda and S mu. And in terms of the characters, the Kronecker product can be written this way. And it could be evaluating as the sum of the product of characters, evaluating over all permutations and divided by n factorial. And using this character equation, we can easily see that the Kronecker coefficients, they have full symmetry over the three parameters. And that's why, that's the reason we can write it in one line. The other doesn't really matter here. Okay, here's an example using the definition how we can find the Kronecker coefficients. So I draw a character table here. And if we are looking at the tensor square of chi2, 1, it's easy to see that A is just a direct sum of all the three irreducibles. And by definition, that means the Kronecker coefficients corresponding to 2, 1, 2, 1, and nu is equal to 1, for nu being equal to 3, 2, 1, 1, 1, 1. Yeah, but in general, this will be very a hard way to compute it. And another simple property of the Kronecker coefficients is that notice that if we have sign character, if I have sign representation and we tensor it with any partition, it will give us a conjugate. So therefore, the Kronecker coefficients has the transposition property. Namely, we can do the conjugate of any two of the partition triples, and the Kronecker coefficients will remain the same. And the little Richardson coefficients are also multiplicities, and they are kind of the analog in the GLN group. And the irreducible representation in the GLN group are the well modules. And they are also indexed by partitions, but this time of infinite dimension, like the only restriction is that their length is less than or equal to n. And the little Richardson coefficients are defined similarly as the multiplicity. And combinatorially, we have a complete understanding of it. We can interpret it as the number of little Richardson tableau of the skew shape new skew mu and the type of lambda. And the little Richardson tableau are just we need to have weakly increasing rows, strictly increasing columns, and the reverse reading word need to be a Baloch sequence. And here's an example for that. So in this case, for this partition triple, we have two little Richardson tableaus, so we can count it. The little Richardson coefficients is equal to 2. And the little Richardson coefficients are actually a special family of the Kronecker coefficients. So this was found by Murnaghan, and you find that, so the difference is that the partition triple we have for the little Richardson coefficients, they are of different sizes. So the size of lambda and mu add up to the size of nu, but in Kronecker coefficients, the partition triple, they are all of the same size. So if we add a long first row to the partition triples, the parameters for the little Richardson coefficients to make them of the same size. And if the first row is long enough, then we are gonna have them equal to each other. And that's also called the reduced Kronecker coefficients. And implies the Kronecker coefficient is stabilized if you have a long first row. And because the little Richardson coefficients, they can be recognized as a special family of Kronecker coefficients, and we have such a nice combinatorial interpretation for them, a natural question would be, can we find a positive combinatorial interpretation for the Kronecker coefficients as well? And this is this question was first raised by Murnaghan in 1938, and it was also listed as an open question by Stanley. Okay, so, but this question is still remains open till today. And little progress has been made towards it, and I'm gonna review some of those. So in 1989, Ramo studied the case where we have two hook shapes in the Kronecker coefficients, and when we have one two-row partition and one hook shape. And later on, Ramo and his student had in 1994, they gave a formula for the case where we have two two-row partitions, but these formulas involve some plus and minuses. So there are some cancellations, and we cannot really use it to determine positivity or the size of the Kronecker coefficients. And this case was again studied by Joanna Blasek and Momoli and Sohoni in 2013. And this time they construct some quantum objects, and they were able to give a simpler and a positive formula for it. And in 2006, this was the first combinatorial interpretation was found by Cristina Valentin and Rosa Orellana. And this they study one of the three partitions is a two-row partition, but it's very restrictive. So they require the first row to be pretty long, longer than twice the second row minus one. And they define something called the Kronecker tableau that describe this this numbers describe, but it doesn't really generalize. And then in 2012 and 2014, Joanna Blasek and Ricky Liu, this is by far the most generalized case we have. So they find a combinatorial interpretation when one of the partition is a hook, and the other two partitions could be anything. And the object they used is a color tableau. And as I mentioned, we have a reduced Kronecker coefficients, and there's also some work regarding those. And but they are all about very special cases, and there are also some other special cases using representation theory techniques. And before we move on to the positivity, I want to show another interpretation for the Kronecker coefficients using some symmetric function techniques. So let's do some review on the identities. So we have this well-character formula for the Schur functions is given by the determinant of a larger matrix over the Vandermonde determinant, and then the Cauchy's identity, which could be put by the RSK. And this looks like the Cauchy's identity, and we call it a generalized Cauchy, which involves the Kronecker coefficient. So if we do the sum over S lambda of X, S mu of Y, S mu of Z, with a weight of the Kronecker coefficients, G of lambda mu nu, this will be equal to the product of 1 over 1 minus Xi, Yj, and Zk. And another way to recognize the Kronecker coefficients in the Schur polynomial is when we evaluate it at xy, which is all pairs of products for x and y's. So this is in some sense like a process expression. And we can see if we combine the Cauchy identity and this last version, we are gonna obtain the generalized Cauchy. So if we multiply both sides by S nu of Z, S or S lambda of Z and sum over lambda, we are gonna get the same thing. Okay, so if we start with the generalized Cauchy and multiply both sides by the Vandermonde determinant, the left-hand side could be simplified to this sum of the Kronecker coefficients multiplied by 3 determinant. And because we standardize the exponent vector, we can equating the coefficients for the monomials. And this gives us an interpretation for a formula for the Kronecker coefficients in terms of the 3-dimensional contingency table. But as we can see, this is like an alternating sum. So it's very hard to tell the positivity or the size from it. And the 3D contingency table, the inputs here are just the size of the slices of it. And here's a maybe example for it. So if we use this to compute the Kronecker coefficients 2, 1, 2, 1, 2, 1, we can expand it in this way and count the number of 3-dimensional contingency table for each of the case. And yeah, we can tell it's not a good way to count. Okay, so let's move on to the next part. I'm gonna talk about something about the positivity of the Kronecker coefficients. So as we see, we made little progress towards finding a combinatorial interpretation. So we kind of switch it to look at the positivity of the coefficients. So in 2012, Haley, Saxo, Tiep, and Zaleski, they proved that for a finite simple group of Lie type, we have this, the Steinberg representation of G contains every irreducible representation of G. And they further conjecture, made this tensor square conjecture saying that for in the symmetric group, for every n except for 2, 4, 9, we have an irreducible representation such that the tensor square of this representation contains every irreducible representation of Sn. And in terms of the Kronecker coefficients, we are saying that we have a partition lambda such that the Kronecker coefficients G lambda lambda mu is positive for every partition mu. And then in 2002, Saxo make this conjecture saying that if we are a triangular number, then a candidate for the tensor square conjecture is the staircase strip. So the tensor square of the staircase strip contains all the other partitions in the oven. And ever since then, some results are people are working towards this Saxo conjecture. So Greta Panova and Yopat and Valahode in 2013, they show that for a large M, all hooks, 2-row partitions, and some partitions with 3 rows, or with 2 rows plus an extra column, they are contained in this tensor square of staircase shape. And Christine Ikemea in 2015 shows that the partitions that are dominant comparable to the staircase shape are constituents of this tensor square. But so this is a useful condition, but if we consider the set of partitions that are dominant comparable to the staircase shape over the set of all partitions, the set will go to 0 as m becomes larger. And then in 2016, Luo and Selke, they show that the tensor force power of this staircase shape contains every irreducible representations of Sn. So they consider it from another perspective, they raise the dimension, and they use some probabilistic method in it. And then in 2017, Christine Basil wrote shows that all double hooks are constituents of it. And then in 2021, Lee shows that all triple hooks are constituents. And last year in 2022, Riva showed that this tensor 4 square could be further worked towards the tensor cube. And this proof is based on a result from Luo and Selke.
When you say double hooks, triple hooks, you mean like a Durfee squares size less than or equal to 3?
Yeah,
No,
that presents.
They're also like hooks, like you don't have a one row longer than the
Yeah,
other.
like something like this.
Ah,
Yeah, it's very restricted.
okay.
Any other questions? Okay, so we don't really have much tools to work with, and the most powerful tool we have to prove positivity is the semigroup property of the Kronecker coefficients. So if we are given two partition triples that gives us positive Kronecker coefficients, their horizontal sum will gives us another positive Kronecker coefficients. And in fact, this horizontal sum is greater or equal to the max of the two ordinal one. The max.
So you only need one of them to be positive.
Well,
if they are
yeah,
positive.
they need to be.
Okay,
positive.
thanks, sorry.
Yeah. So here's an example of the horizontal sum. So we just add them piece by piece from top to bottom. And because we have the transposition property for the Kronecker coefficients, this is an equivalence thing. We have this also follows. We can also do a pair of vertical sum and one horizontal sum. So we cannot do 3 vertical sum. Okay, so then in 2020, Christine Basil and Greta Panova conjectured that for every n, there exists a k of n such that the tensor square of every self-conjugate partition whose Durfee size is at least this k of n, and is not the square partition, satisfies the tensor square conjecture. So if that's saying that if a self-conjugate partition is fat enough, then it may satisfy the tensor square conjecture. And as we can see from the property, the way we add it up in the semigroup property, we can consider the rectangular or the square shape as a fundamental building block for it. Because that's the case when we want to split it, decompose it into 2 other partitions. We can only decompose a rectangle into rectangles or squares. And so what I look at is the tensor square of the square shape, and we wonder what happens there. And we know it doesn't satisfy the tensor square conjecture, but we conjecture that it's gonna vanish only on a finite set listed here, but it's gonna be positive for all the other partitions.
How do you check that?
So I use Sage.
But how far did you check it?
How far?
Yeah.
I
How-
check it up
what did you do
to
to check it?
7.
So
The
you
side.
conjectures for n greater than equal to 8.
Yeah, but we have some no result for n greater than or equal to 8 for other special cases. but
Okay, so you
with-
haven't computer checked it for m greater than equal to 8
No.
or anything, but you have some special cases and you think it's true in general. Okay.
But the 8 is the size of the square, so this is the Kronecker coefficient for the symmetric group of size 64.
Right, as
No,
I was,
but, yeah.
I was wondering, like, what's the evidence for the conjecture, right? And then you said you computer tested it, and that's striking, but I guess not.
No, we cannot really test beyond for everything, basically.
Right.
We can only infer various things.
So those are some known results. So it was proved that if we have a set length greater than or equal to 7, it contains all the hooks except for those ones. And if we have a square of size at least 8, then it contains all the 2-row partitions. And this was actually original study. This also works for the rectangular case. So if you have M and N there, this formula still works. And so with using the known result, if we fully prove the forward direction, so that's the Kronecker coefficient will be 0 for the partitions in the set. So this known result proof cover the hook shapes. So we show that it's also 0 for the 2 3-row cases. And to go for that, we give a formula for the Kronecker coefficients. We compute it when the second row is relatively short. And this Kronecker coefficients will be equal to the sum of the number of distinct part of partition alpha of k minus 1, with the first 2 parts being equal, minus the number of partitions of k with no parts being equal to 1 or 2. And we derive this formula using, like, we start with the Pierre's rule. We can rewrite this 3-row partition in terms of some 2-row partitions and product of known results. And we can rewrite this Kronecker coefficients as some differences. And then using the Littlewood's identity and Jacobi-Trudi, we can rewrite it in terms of the Littlewood-Richardson coefficients and do the computation. Yeah. So given this result, the first thing we can do is we can plug in and check when k is equal to 2, 3, or 4. This Kronecker coefficients will be 0. And when k is larger, there is a natural injection from the set of all partitions with no parts being equal to 1 or 2, and the set of partitions k minus 1 with the first 2 parts being equal. So we can just remove one cell from the last row of beta and do the transpose. And this shows that the Kronecker coefficients is positive for k between 5 and m. And so, but this doesn't work for larger k because it wouldn't simplify as well using this equation. So we want to extend this case for longer second row, and we prove it using the semi-group property. We divide it into 2 cases based on the parity of m. So when m is even, we prove by induction. So we decompose it. We decompose a larger rectangle with even size into a smaller rectangle, a smaller square with even size, and 2 by m rectangle and 2 by m minus 1 rectangle. And then using the result from Ramo and Whitehead. So the Kronecker coefficients G, N, 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 mu is positive if the third partition is either has less than or equal to 4 parts and all parts being even, or they have exactly 4 parts and all parts being odd. So all we need to do is to find a way to decompose the partition of this type into some serial partitions and some partitions of even parts. And this doesn't work for the odd case because it's hard to, you will face some difficulty if you want to decompose a partition of size 2 times an odd number into a partition of even parts. And what we did instead is we actually need to break down into some further cases. But for instance, for one case relatively large and M is odd, what we did is we decompose it into 4 rectangles of roughly the same size. So for instance, this case where we have M being 17, we can decompose it into an 8 by 8 square and a 9 by 9 square and some 8 by 9 and 8 by 9 rectangles and prove it by induction. Okay, so once we have those, natural generalization is if we can prove the positivity for all serial partitions, we can use a similar method as how we deal with the even numbers for this case, when we have an even side and the third row being greater than or equal to 2. But in the odd case, we can do a similar method to cover most of cases, but there are some side cases that couldn't be done for. Okay, so the next family of partitions we look at are the near hooks. By the near hooks, we say a partition as a near hook is if we have a hook, we add 1 box here or 2 boxes, so we can add 1 or 2 or a few numbers of boxes here. So in particular, in this case, I first look at the case where I just add 1 box in a hook. And we show that, so this is a sufficient condition for it to be positive. But so if K is not in the set NK2 of M, then the Kronecker coefficients of this near hook is positive. And this is proved by using this tool developed specifically for proving the positivity in a sexual conjecture. So if mu is a self-conjugate partition, and we consider the principal hooks of mu, then we found the Kronecker coefficients lambda mu is bounded below by the absolute value of the character, evaluating at mu, evaluating at the principal hook. So in particular, the principal hooks of our square is 1, 3, 5 until 2n minus 1. And the shape we are looking at is this near hook shape. And we consider computing the character using the Murnaghan rule. So we consider the ring hook tableau. And there are only 3 ways to place the hooks of length 1 and 3. And therefore we can rewrite the character in terms of the number of ways to occupy this longer side or this part using the rest of the parts. So from 5 to 2n minus 1. And we do a similar thing for the case where we have 2 blocks below the first row. So the second row has a length of 3. And in this case, there are only 2 ways to place the 1 hook and the 3 hooks. And we can rewrite the character as the sum of 2 partitions with the restricted parts. And so we just need to find for which cases those are positive. And except for numbers being equal to 1, 3, m squared minus 5, m squared minus 7, we can show that the Kronecker coefficient is positive. Okay, so before I move on, are there any questions? Okay, so the last part I want to talk about is the Newton polytope, the saturated Newton polytope. So the Newton polytope of a polynomial is the Convex Hall of the set of exponent vectors of its monomials. And we say a polynomial has a saturated Newton polytope if every lattice point of the convex Hall of the exponent vector are appears corresponding to a monomial in the polynomial. So yeah, so one thing is not every polynomial has SMP. So for instance, if we consider this polynomial x1 cubed plus 3x1 x2 plus x cubed, the vector, the exponent vectors are 3, 0, 0, 3, and 1, 1. And 1, 2 is a lattice point there, but it's not appears there. So this is not a separated one. And the Schur polynomials, they are saturated Newton polytope as we can find the unique maximal term in the monomial expansion. Okay, so Monica, Tolkien, and Young, they study the saturating Newton polytope over like all possible polynomials and quasi-polynomials in 2017. And they make this conjecture saying that the Kronecker product of two Schur polynomials is SMP. And they check up to n equals 8 or 9. And we check this conjecture for up to n equals 18. And we show that if we have two row partitions of n, then the Kronecker product of the Schur functions of those two row partitions is saturating Newton polytope. And we prove this by showing there is a unique maximal term in the Schur expansion. And whenever you have a unique maximal term in the Schur expansion, it follows. And we also prove similarly for the case when we have a 2-row partition and a 3-row partition. We need to have the first row of the 2-row partition being smaller, because otherwise, so in this case, again, we can find the unique maximal term in the Schur expansion. But if we switch around, if we have mu1 being greater than mu1, then it's possible that we don't have a unique maximal term. So here's an example one.
But for this one, you could actually just check. Does it have SMP?
Yes, we can check, but if the n increases, it's become.
Well, I'm just asking, is this a counterexample?
Oh, no, this is not a counterexample.
Okay.
Conjecture's too hot.
Right, just checking.
Yeah, but this is an example for when we don't have a unique maximal term and it still has SMP. Yeah. So here we have 6, 6 appears and 8, 2, 2 appears, so there's no unique maximal term. Yeah, and so the question is we want to show a Kronecker product. We want to determine whether it's in SMP even if we don't have a unique maximal term. So that's all I have for today.
That's awesome. Any questions for Chenchen?
For the like saturated Newton polytope, the like example with like Schurs into monomials, it seemed like well, like having that property told you something about when the coefficients are non-negative? Is that like the, I guess I'm curious why the, like, how the, like, having a saturated Newton polytope like applies to the like problem of like determining non-negativity, or like, or does it even like give you a combinatorial, or like would help towards a combinatorial interpretation?
So you are saying,
Can you relate the second and third halves of your talk?
yeah. Oh.
So there is one way in which you can, if you know that you have a saturated Newton polytope, you know that you can, if you, let's say, know the convex hull or whatever, you choose a monomial that is there, you know there is going to exist a partition whose Schur expansion contains it, so there's going to be a dominant. So it's going to dominate whatever monomial is. You're going to have a positive Kronecker coefficient, but it's not going to.
Well, it doesn't tell you which Schur polynomial.
Yeah, exactly. But most of the things with Kronecker coefficient, you're not going to guess which exactly are going to be positive, because
Yeah.
Complexity problem. So, but that's one of the. That's one of the connections and motivations. It has to do with positivity, but not even only.
This is nice, because I didn't think these guys in that paper, I mean, they really didn't motivate.
Yeah.
They didn't give any evidence for this conjecture, except that they kind of fit the pattern. It would be nice. So it's nice that you guys actually finally have some evidence for this wild guess, also called conjecture.
Yeah.
It seems like they nailed
So
it.
I tried to disprove it for quite a while.
Oh, that's even more evidence. Okay.
So
Because they didn't have any evidence for it. They just sort of guessed.
yeah, all these nice things in algebraic combinatorics should have this.
Right. Yeah. This is love. This is great. I didn't know there was any evidence for it now, so this is great. Any other questions for Chenchen?
What if you took the Kronecker product of SNPs that weren't Schurs?
Huh?
So what if you took some symmetric polynomials, took their Kronecker product, say with non-negative coefficients, took the Kronecker product, like, would you expect the result to still be SNP? Or is this
You're
special to
asking
the
if it's
S-line?
closed under Kronecker producting?
Yeah, I guess. Yeah, roughly speaking, is SNP conjecturally closed under Kronecker products?
But actually even with negative, I guess.
I know it's not even close under squares.
Okay.
Yeah.
Yeah, that's a hard no on that one. Okay.
So squares and
But,
Kronecker squares are different.
Yeah, but if you, I guess you're saying that if you take a polynomial that has SNP and you square it, it's not guaranteed to have SNP.
Yeah.
But that's
this
not
is
the Kronecker product, I guess,
Yeah.
is Josh.
I would guess it would fail, like, but I was just wondering.
Yeah, I haven't think about it. But yeah, maybe.
I mean, you guys would have to think about it because they did. That's an interesting question.